All right, let's take some notes on distance. So distance is the distance between 2 points. If I wanted to say, hey, what's the distance between points A and B, the ones I have over here, I could either write that as the length of AB, segment AB, right? Notice that this line here has no arrows on the end of it, so this means that we're talking about the length of the segment that starts at A and ends at B. Or you can write AB with nothing above it, and that indicates that you're talking about a distance. So I could look at my problem over here, and I could say, okay, AB is equal to, and, nothing too groundbreaking here. If I want to go from -1 to 3, I'm going to go 4 units. You could do 3 minus -1. You could take the absolute value of -1 minus 3. Either way, it's 1, 2, 3, 4 units. So AB, again with no notation above it, is 4. We could also talk about congruence. So congruence is a new concept for us here. If I have a segment or the length of the distance between 2 points being AB and the distance between 2 points CD, if they are equal to each other, meaning they're the same thing, and sure enough, I can look over here and see that CD is indeed equal to 1, 2, 3, 4 units, then the fact that they are equal in distance means that the segments are going to be congruent, and we have some symbols that we can use to show that there's congruence between those segments. Segment AB is going to be, and here's what it is. It's like an equal sign with a squiggly over the top of it. We read that as is congruent to segment CD. All right, you can also take some of these distances and you can add them together to equal other distances. So for example, I have A, B, and C. They are collinear, they are on the same line. And if B is in between A and C, notice what that does for us. That gives us a segment here of AB, that gives us a segment here of BC, and we can talk about the distances of these as well. That distance from A to B, if we add that to the distance from B to C, that is going to give us the entire distance, right? The total distance from A, so A to B plus B to C gives us all of A and C. Okay, so that's going to come in handy whenever we work on a few algebra problems in the near future. Okay, and we are going to be looking at distance quite a bit on the coordinate plane. You can see I've already worked out a couple problems here, but I want to focus on this one first. So our first kind of introduction to the distance formula, let's say I wanted to find the distance from between these 2 points, the ones that we have graphed here. We have actually learned a way to do this in the past, right? This is simply the hypotenuse on a right triangle. Check it out. I can take the change in vertical distance and the change in horizontal distance and create a 90-degree triangle. What can we do with 90-degree triangles? We can use the Pythagorean theorem to figure out what that last side is. So I basically have a side A and a side B and a side C. Now, what are those distances? Side A is 3 units. Side B is 1, 2, 3, 4, 5, 6 units. So we can plug in to A squared plus B squared equals C squared. A squared being 3 squared, B squared being 6 squared, and C squared being our unknown. 3 times 3 is 9. 6 times 6 is 36. Still equals C squared. 9 plus 36 is 45. Still equals C squared. We are going to use the square root property of equality, which means that you can undo that exponent using a square root. The inverse operation of something squared is taking the square root, so that's going to cancel that out. And then the square root of 45, we can either leave as the square root of 45, we can simplify that down into like 3 times the square root of 5, or we can just write that as a decimal. Let's say that that is about 6.71. You can use a calculator to figure that out. That is about the length of C. So that's one way to work this out, is by using the Pythagorean theorem. I think it works great, especially if you have a picture. It's easy to kind of draw the triangle and visualize that in order to solve using that formula. We also have something known as the distance formula, which will do the exact same thing. And you'll notice that this is going to be the actual formula here. It sort of like skips some of these steps and gets us straight to this point right here where we are taking the square root of those distances squared. So the distances being, in our case, 9 and 36, added together being 45. It kind of just jumps to the square root part of the problem. So if I envision this point up here as x1 and y1, this one down here is x2 and y2, right? These are ordered pairs. Then this distance of 3 is this x value of -2 minus this x value of -5. So this distance is -2 minus -5, which of course is 3, or x2 minus x1. And you square that and get 9, and then you eventually add it to this distance over here. I've got y2, which is -3, y1, which is +3, -3, -3 does give us -6, but whenever you square -6, guess what happens? You get 36, and then that 9 plus 36 equals 45. If you plug it into here, like I said, it just kind of jumps you straight to this step here. So this is your official distance formula. I would recommend making sure that is written somewhere because it's kind of your shortcut to solving a lot of these distance problems on the coordinate plane. All right, let's take a look at an example problem here. I've got points. I've already solved this one here, but let me show you how I got these answers. So -4, 1, put a dot there, 3, -1. Remember, you go left and right first and then up and down whenever you're plotting these points. If I'm trying to find this distance, I can create a right triangle using the side lengths of 2 and 7. And of course, that would be helping me find the distance of the hypotenuse between those 2 points. So that would be my C value here. So that's how I end up plugging in here. 7 squared, which is 49, 2 squared equals C squared. 49 plus 4 is 53, and the square root of 53 is about 7.28. Now, what does that look like whenever we use the distance formula? Remember, the distance formula is the one that we were just given over here. We kind of derived from the Pythagorean theorem. What that would look like, so let's put a big or. You could do it this way. You could say, all right, let's go back to our coordinates up here. You could say, okay, well, what if this is x1 and y1, and this is x2 and y2? So these are the x and y coordinates of point 1. These are the x and y coordinates of point 2. How does that plug into our formula here? So x2 minus x1, that is going to be 3 minus a -4, and we're going to square that. Add that to y2, which is -1, minus y1, which is +1. We're going to square that. And once we've done all this math, it's going to equal that distance. So 3 minus -4 equals 7. Oh, no surprise there. That's what we got as our distance already using this other method. -1 minus 1, better not forget that exponent. -1 minus 1 is -2, but we're going to square that in a second. So we're going to, even though here we got 2, well, 2 times 2 is 4, and -2 times -2 is also 4. So we're going to end up with the same answers anyway. All this still equals D. This is going to be 49 plus 4, taking the square root of that, equals D. And like we said earlier, this is going to be the square root of 53, which has already been established to be about 7.28. And that, sure enough, is the distance between the 2 points that we are asked to find. -4, 1, and 3, -1. All right, hope this video is helpful. I'll see you in class.